Okay, welcome everyone for today's quantum space-time seminar. We are happy to have Subir Pujabi from IIT Bombay. He's going to tell us about properties of anticommuting quantum spin liquids.
Thank you, Abhijit, and thank you everyone for coming. So I actually gave a talk on this topic last September. At that point, I didn't know enough about what I was talking about. Now I know a little more. So I was talking about this object called anticommuting quantum spin liquid, which I'll recap a little bit and then try to tell you what are the interesting aspects about it. And please feel free to stop for questions and all that, right? Yeah. So the last time, as I said, because I didn't know what I was really talking about, I was trying to give some background as to where it fits maybe in the general classification or some kind of categorization of various kinds of vacua that you might have and the excitation spectrum on top of that. This time I have a little more idea, so I'll focus more on results. However, I'll quickly recap what I talked about last time. So the prototypical model, if you wish, and this is going to be some, lattice Hamiltonians. You can think of them some qubit codes from a quantum error correcting point of view. Okay. Essentially, spin half degrees of freedom on a square lattice. This can be a prototypical model. So let's put on the following pattern. And so on. So imagine you have a pattern of x's and z's like that. And now we'll write a Hamiltonian. So on the x plaquette, so the muth plaquette, I'll have some local Hamiltonian for that plaquette. So one local Hamiltonian you may imagine is just a simple Ising chain. The nearest neighbor bonds belonging to this plaquette. With some coupling constant. Let's put it there. Something like this. Okay. But it need not be this, but this is one classic example, or you could just have the product of the four mu's on the plaquette. Can do many more variations. They are important for the physics at some sense, but there are some generalities that once you have this kind of structure, you can say some general things already, which is what I was focusing on last time. Let me recap that real quick. So let's maybe take this for argument's sake. So I have these Ising chains along x direction on these plaquettes and along z direction in these plaquettes. So these are what we call in quantum matter Z2 symmetric models. In the Hilbert space, it subdivides into two sectors, where in one sector you have even number of downspins, in the other sector you have odd number of downspins, and the Hamiltonian cannot connect across the two. But what we are interested in is, if you wish, the algebra of the conserved quantities in this model. Okay, so even there was a discussion last time. I think Shiraz sort of put it in focus, which was the idea that once you are given the symmetry of your conserved charges, etc., you can repose the question as what are the possible representations of that algebra. Okay, so we will sort of take that point of view. Maybe you can keep that in mind. But let's write down what is this algebra. So this is what I call the decommuting algebra or structure. So I'll write down the conserved quantities. So on the x plaquette, you have the following conserved quantity. The product of the four sigmas in half Pauli matrices. This, it turns out to be a conserved quantity. You can check it fairly easily that on the plaquette, you have pairwise anti-commutation. so it commutes. And the links outgoing from the plaquette are made of sigma z's. They also commute. Okay.
Wait, so if you had sigma x's, then also it's okay, right?
Sigma x won't commute with the outgoing z link.
But there are two of them always.
But right now I have the sum. Right, so I have to commute with each term. So for this product, let's say I'm focused on this one, the product of sigma x's has to commute with sigma z, but it won't because there's only a single anticommutation. Yeah. Yeah.
If your the Hamiltonian term for a blank plaquette is
Right now, not. Okay. But yeah, that's the construction. And there is a similar conserved quantity on the Z plaquette. So the way to think about it is if you are familiar with quantumizing models and such like, this is like a local Z2 parity on each plaquette. Okay. So the quantumizing model has a global Z2 parity. This is the local version of that. So this is again the symmetry algebras and their representations. Okay. So just because you said that, let me just mention, and this is more from a condensed matter point of view where we are trying to construct lattice models which might be interesting. As is often the case, right? You might be trying to construct some continuum model. We are trying to construct some lattice models. And as I wrote in my abstract, maybe another point of view is these might be what has been called qubit regularization by Sailesh Chandrasekharan. There's a way to regularize, if you want to simulate a lattice gauge theory or some object of interest for you on a quantum computer, how would you do that? So there's an idea of qubit regularization. So there's that point of view that these models might be interesting. I don't know, but maybe they are qubit regularized versions of some objects of interest for you, possibly. But from a condensed matter model construction point of view, we can sort of, where this fits, if you wish, it's a cross-linked, sort of in some interesting way, you have cross-linked Ising chains, Ising plaquettes. An Ising model is a very sort of, has a very non-trivial structure to it. So if you can sort of, do some cross-linking of some sort, it might lead to some interesting physics. That's one way of thinking about the model construction aspect. Another famous example is the Kitaev honeycomb model. You need not worry too much about it. I will make some connections to it. It kind of naturally fits into this category of, Ising chains or Ising objects kind of playing, cross-talking. So in Kitaev model, you have a sigma x. So it's a honeycomb lattice model. You have sigma z, you have sigma y, and you translate it. Okay. And so you can think of it as, Ising bond units cross-linked in some way. Here it turns out the Ising parities are not conserved actually in this model. The local Ising parities are not conserved. So it's not trivial in that sense. But it kind of has that spirit. I've taken some basic Ising objects, Ising plaquettes here and cross-linked them. As it has cross-linked, Ising bonds in some interesting way. It turns out this is solvable. And this trivalency and orthogonal direction in spin space is pretty much the only non-trivial thing you can do, it turns out, if you want some solvability. So, but let's focus on this.
What is the charges, local charges?
There are no local charges which follow this anticommuting. There are some local charges which is a hexagon plaquette term. They all commute. It turns out because there's a pairwise anticommutation there. So it does not obey.
So the key difference is here the charges come, here the charges
don't come. Yeah.
Sorry, where the charges come
in the Kitaev form.
Okay.
That's the case we are kind of used to.
And the charges commute with the Hamiltonians.
Yes.
Each other.
Yeah. So I can write down the chart. So you focus on these things. On this side, you look at the outgoing link, just as the same idea here. So if it is outgoing is y, so sigma y डालो. Outgoing is whatever, तो वो डालो. छह product होगा, it will all pairwise anti-commute and commute with the rest. But two ones also pairwise anti-commute. So it's a commuting algebra.
Pairwise commute.
Pairwise anti-commute.
Pairwise anti-commute.
If they are nearest neighbor, of course, when they are farther, any commute. Yeah. But from a model construction point of view, there are similarities. You're taking Ising objects and trying to do something. In fact, there are simpler
Just making sure that Z and the X plaquettes share only
one side. Yeah, from a just yes.
construction point of
Yes,
view.
yes.
That's why you have anti-commuting and you don't have pairwise things that.
Right. So you can do the same thing. This is prototypical. We will stick to this, but I can just say that you can take an Ising bond and connect it to that triangle. This is Z, this is X maybe, and you can keep doing this. This is another thing which will actually obey this. You can do it with triangles, which I'll talk about later.
Yeah.
But this is a general idea.
Key point is they should share only one
Side.
vertex.
Yes.
Yeah.
Exactly. So now,
So can you do this construction in 3D as well? Or is it
Yeah.
something special to do?
No. You can do it in any dimensions. The local Hamiltonian structure, you are agnostic to that as long as you have some local Z2 parity.
Yeah.
Yeah. Now let's just recap the anti-commuting algebra.
So one more question.
Yeah. Yeah. Yeah.
There are condensed matter.
Hmm.
Is there a, like in Kitaev models, at least in some materials or in some old atom history, there is a people have at least proposed ways to get this.
Right.
Is there a way conceivable that we will be able to generate this Hamiltonian where alternate things are existing?
I don't know. That's a question in quantum chemistry itself. Like, can you imagine an orbital in a crystal environment which arranges for this coupling? That's a question, valid question. I don't know the answer.
No, because the question would be about that vertex, even when you do orbitals, right? You're
Right.
saying that
Yeah.
in one,
Yeah.
two directions,
Yeah,
it
yeah.
should only couple to X.
Correct. Yeah.
And in two directions,
Yeah.
it should
Yeah.
only
Yeah.
couple to Z.
Exactly. Is there an easy axis coupling in orthogonal directions in spin space? Can you arrange for that? That's a quantum chemistry question. But I won't go there. So, but let's look at the anti-commuting algebra now. So let's take these two plaquettes. On this plaquette, I have this. On this plaquette, I have this. They share a site. On this site,
Yes, for Rajiv's question, if you're lucky, somebody like geometrically will find something.
if I'm lucky.
I remember Kitaev first talked about the Kitaev model in 1999.
Right.
And I think Jekyllin is
2009, 2008 or whatever. Yeah. So
a while for people to get interested.
true,
Only
but
people are interested will they think
No, but in the gold atom community, people had it.
Gold atom to alag baat hai.
No, I'm saying the reason being that there you are much more flexible.
Gold atom you can emulate what you like.
But can you do this? I'm not
no,
so sure.
but no. Coming to the emulation point, actually, that's the general direction the community at large is going, and I personally subscribe to that, which is, of course, maybe there might not be a material realization
No,
of it.
in fact, I was not asking you about a material. I was asking you
Artificial realization,
how.
you can put it on some sycamore. I don't know. I can't do it, but someone can, I'm sure. Yeah.
I'm saying don't be so. Once you're given that flexibility, it's kind of useful to come up with a scheme, either with sycamore or with.
Those are valid questions. That's not my concern, but those are valid questions.
Materials may be hard.
Yeah.
I agree with
Yeah. Those are valid questions. There will be legitimate answers. It's just I'm not focused
Yeah, I
on
think if the Kitaev model had only been emulatable on a gold atom system, there wouldn't be the explosion of it.
Right.
It's Jekyllin that really
True.
made a mainstream thing.
True. But Kitaev's toric code, and Kitaev's toric code was not motivated by materials. It's really a quantum computer motivation, and all these things, I'm not going to get into that, but there are legitimate, valid quantum error correction, quantum code kind of motivations for these things, which I am studying separately. But let's get back. So these two conserved quantities on these two plaquettes, suppose they came from two different plaquettes, obviously they commute, their standard spin half. But when you are like this, they share a site. One quantity brings the sigma z, the other quantity brings the sigma x. So therefore they will anti-commute. So there's only a single anti-commutation. Everything else is a commutation, right? So we just calling it like this, and there was that plaquette here. These two anti-commute. Okay, so this is the recap of what anti-commuting algebra stands for. You can arrange for this in different kinds of construction. You just have some basic Ising units, you cross-link them on site sharing. structure. You need a corner sharing or site sharing structure instead of a bond sharing structure. And so you can do the same thing on Kagome lattice. There are many corner sharing lattices where you can do that. If time permits, I'll tell you one interesting aspect when you do this whole thing on a non-bipartite lattice. So given this much,
As a side question, what is this lattice called? Name.
I mean, it's based on the square lattice, but the unit cell is this big, with 4 sides per unit cell. Not that I'm aware of. Yeah, not that I'm aware of. It's like a decorated square lattice, you can think of it. Yeah. So what are the consequences of having this kind of a general structure? Note that every plaquette has this. So there are an extensive number of these local conserved quantities.
And can you add to it extends terms, or you should not have extends terms?
Like S dot S, Heisenberg exchange. No, that will break the structure.
That will break it.
structure. Yes, that will break the structure. So this immediately leads to the following two things. Extensive degeneracy.
Then if you just leave it Kitaev, that was the big thing about Kitaev. It came out of exchange, modulating exchanges in direction, but it was all exchange.
Right.
Which in the end is where, I mean, it would be very hard to think of a material where I have plaquette, but no exchange.
Right.
Wait,
Right. No, it is
he has only exchange.
He have only Ising exchanges.
There is no plaquette interaction.
What
I thought, oh,
The charges are plaquette.
charges, but your Hamiltonian
there
is.
is Ising exchange.
Oh, okay.
Oh, no,
I
no.
was thinking you were.
No, when you said exchange, I thought Heisenberg exchange.
That's the whole point of one connecting.
Okay.
Yeah. The Heisenberg exchange, we have Ising exchange, so it's a bond-dependent coupling.
Mhm.
That's a harder thing to arrange for materially, right?
Okay,
So-
no, that's fine, yeah,
Yeah,
okay, good.
So you have an extensive degeneracy. It turns out that this has 2 to the number of unit cells for this model. Okay. It turns out this is the count. So the counting, as you can see, is just 2 to some number. So it's not a complicated counting. It's a simple counting. There are some other situations like classical spin ices where the counting is actually very interesting from a counting point of view. Here it is simple. But this also leads to what
Why is there no extra two in the new exponent?
यहाँ पे there, two times number of units.
Because there are two x.
So the point is these two, yeah, there are 2 charges, but they don't commute. So you have to stick to one set of charges,
Okay.
and then the other set generates a degeneracy. So this we had, this is the funda basically. But beyond this extensive degeneracy, and it often happens whenever, even in classical context, if you arrange for a lot of degeneracy, the degenerate manifold, when you are sort of doing an ensemble sum or something over them, it leads to loss of magnetic. No magnetic correlations can survive that. So something like that happens here. You take 2 sides, need not be very far, but let's take, for argument's sake, 3 sides. And any 2-spin correlator of this form actually is 0 when you sum over the manifold. Okay, there are the cancellations in the problem. So this is what is often considered as a form of liquidity in the spin variable. This is a magnetic order. So let's just get what we mean by this. So so let's say if this was a 4x4 system, then there are 4 of these. So you will have 8. 4 to the power 4 is 16. So 1, 2, something like 16 states. Now there might or might not be a gap to this, but any eigenstate will be so much degenerate. So this degeneracy at a spectrum level. And this is a side comment. I don't want to get into it today, but you might wonder that this is a very special algebra. It can easily break. And so the general, let's say, philosophy is that if you break this structure a little bit, you will still see the physics of this extensive degeneracy because it will form a small band. So the very high density of states when you go away from this sort of special structure. And that structure might have consequences at that energy scale.
But that's only when you are gapped.
Yeah.
If you are gapless, then this band will make sense.
Yes,
Then
yes,
you
yes.
cannot,
Yeah.
then breaking is much more fragile, right? Because suppose your thing has come down here, then I
Right.
make it a band, everything will mix.
Yeah, but when you mix, you only mix more, maybe. I don't know. Yes, I see what you're saying. Yeah.
So what do you mean this gap or gapness? The Hamiltonian is there, right? It is what it
He
is.
is going to break this exact symmetry.
Now the question is, in the exact model, each degenerate state is gapped. with the next state far away?
We don't know. That also depends on
That
the
depends on what values you give.
couplings, etc.
Right.
Yeah.
But for, let's say I make all of the values the same.
Right.
Then what happens?
Then there it might be gapless.
Is it not?
Maybe it might be gapless. That's my sense. I'll give some argument, but I don't have an exact solution.
But then you diagonalize it or something, it will become gap.
Yeah.
Yeah.
So no, I was saying what his statement that you keep saying this degeneration. His point was if if you
If
break
it's
it
gap,
slightly,
degeneracy is perturbatively fine.
break that degeneracy perturbatively, this 16 will form its own band.
No, but I'm saying even when, let's say, when they're degenerate, why would they be close? Wouldn't they be separated by that?
No, so we are talking of different things. I think the point is you have some 16-fold state, the next 16-fold state.
Yeah.
If they are separated by some whatever thing,
Yeah.
then if you break this algebra by keep it, you will get two well separated.
Yeah.
But he doesn't know whether for particular values of j that he puts in,
Yeah.
whether that's the case
So
or
why
whether-
would it not be the case? That's what I'm
That can, so we'll see actually an example. of
that's
that.
a question of detail he's not answering.
Take the Kitaev model, it has gapless space.
Right. So it's like a phase
It
diagram.
depends on now, it depends on.
Presumably
what
you can arrange to do
That cannot be just a function of your algebra and.
No, I mean the J.
No,
Yeah,
depends on what value of j is.
It
you
will
get.
be controlled by us. So a short answer is suppose one j dominated, then you will have a gap of this sort. If they're equal, you expect
you
them
don't
to
know.
actually. You don't know, but you expect it to be the case actually.
But by that you mean all this, so we are on some finite lattice or
Let's say.
then you would have this degeneracy is 2 to the n and the total number of states is what 2 to the 4n or something.
Right.
So whatever 2 to the 4n by 2 to the n,
Yeah.
that would be the level that
Yeah.
those would be the discrete levels that you would take.
Correct.
And the
Yes.
spacing would be some controlled by some j, right?
Yes.
And then
Especially would be.
so j and n. J
No,
was
so I think
j and
he has one parameter in which is not defined explicitly. There's a jx and there's a jy.
yeah.
As a function of its ratio,
Yeah.
these different sectors could be well separated in a thing or not,
Or not.
right? So he's not told us that.
So that is a matter of detail from this perspective, from the algebra perspective.
Assuming you are in a well separated
Yeah.
sector, what he is saying is correct. If you break it perturbatively, you
Yeah.
should not worry about it.
Yeah.
So, right. So now, it smells like, this is a kind of local gauge charges.
I have always thought of this as a question that if you, given that you have such expensive degeneracy, even if I break things perturbatively, it clear that the effect should remain perturbative.
That's a good question.
I don't know, maybe it is. I'm just saying as a general statement.
I mean, generally, if you have a very high density of
Let it
states,
separated.
No, I'm saying that, see, it will not be 16, it will be 2 to the power n here,
Yeah.
right? And then you break degeneracy or break this, right? I don't know.
I mean, generally, when you have a lot of density of states, anything can happen.
Yeah, that is my.
Yeah. In fact, in the last time we discussed one particular case where you do
Yeah.
something and you can work things out.
You can work things out.
But generally, it's hard to say actually.
So scenario where this breaks.
Like put a small, what we call a transverse field, like just a single side term. Like imagine applying a magnetic field. Then everything goes out the window, this structure.
But like instead of forming a band, what do they do?
They will form a small band. Now, if they're all close together, you'll have a lot of mixing. And
See, how many states are you talking about? 2 to the power n, right? You are not talking about just order 1, what is the next excitation?
Right, but we are familiar with one case at least. We are.
I'm not saying that there cannot be, I'm just saying
In the
that.
Hubbard model at half billion.
Yeah.
At large U, that's 2 to the power n.
He's talking about many body states. If
Yeah,
I
so-
take Howard model, many body states.
So I have 2 to the n.
Yes.
They break
Yeah.
because there is a TB,
Correct.
right? And I get 2 to the n by 2 to the n Hamiltonian, which is well set. All its levels are well separated from the charge states.
What are you saying? Suppose I take the full spin
the
and
large
I
spin.
keep adding the spin waves.
Take the large U. The Hubbard model.
Yeah.
With t equal to 0.
Yeah.
Right, there are sectors based on t. Now you put t in. Each sector remains well separated from the other.
Only for the single particle states. Yeah. if I put the
Maybe-
answer
maybe
is
we-
order nj, no total anybody.
Well,
Is there any relation to the
One
more
particle
model?
state?
yes, it's going to come.
Or maybe a
It's
two
going to come.
particle
It is
state.
related.
Yeah.
I'm saying
So when
suppose
derive the.
I take the Heisenberg
model
model.
and vice versa.
What is the
For this
maximum energy I
for a
can put in
particular
NJ?
variable. I'll talk about it.
When I call the bonds.
Yeah, you're right, you're right.
क्योंकि मुझे
NJ is not smaller
Nice,
than
very
E.
nice. So
Not necessarily.
maybe we can continue
That
because this will.
do in any model.
That's what I'm saying, because he's talking about the whole 2 to the power n becoming a band. I would not have said
Shall I
this if
continue
there were
with
n
that?
states. Right? So then I don't know the answer.
I think we have digressed a little bit, maybe.
I mean, in conventional language, we say the Hubbard model as a charge net.
That's for a single
That
particle.
is the, yeah, but that is the sense in which we also have a gap.
These,
That's the
these
same
local
thing.
That's all.
we are familiar with this. We
We
can
also
also
think
think that
about
this
that.
being gauge symmetric, it should be thought of.
Yeah,
as
yeah, so that is a question. So that is the question. So
That's all.
you might think that these are local charges, so they smell like gauge things, but this leads to degeneracy.
Degeneracy.
But there, as we discussed, there are redundancies and you don't want to consider them. Here, so this is a new result. You will see that the gauge redundancy sort of becomes physical almost, in a sense. And that we can see actually through a nice sort of different way of looking at things, which is whenever you have these Ising models, the Majorana representation often turns out to be a useful thing to consider. For example, this Kitaev model that I wrote, that actually becomes solvable in a Majorana representation. So let me write down that representation. So this is called Kitaev Majorana representation.
Quick question.
Yes, please.
So the spin liquidity is it simply with the gauge thing in mind, the spin
Yeah.
liquidity is simply the same as that's not a gauge that goes into the design.
Yes. Yeah, that's precisely one of the ways of thinking about it. So in our lattice gauge theory, we have the Ellipsoid's theorem. It's kind of a physical version of the Ellipsoid's theorem, that cancellation of everything.
So one question, and this of course all spin liquid people get very annoyed when asked, can this lead to alternate type stuff where you have quadrupolar order rather than dipolar order? But I don't consider this spin correlation for sigma, 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 sigma.
That can be best. That can be. Higher spin correlations.
Should I
Featureless-
call it a spin liquid in the sense that?
No, I don't think it will be of the symmetry breaking type,
Okay.
but there can be higher spin non-zero correlations. Like in Kitaev model also, you have dimer-dimer correlations which decay as power law,
Correct,
but you have to be sensitive to the local energetic.
correct.
Similar things can happen here. They don't survive the cancellations. So that,
But they never order.
as far as I can, that's my intuition. So on any site, you can recast your spin variables in a Majorana representation. So you have the Majorana degrees of freedom. You have 4 Majorana degrees of freedom per spin degree of freedom. So Majorana, if you have worked with these objects, they are sometimes said to have a dimension of √2. So 4 Majoranas work out to be √2 to the power 4, which is bigger than the Hilbert space dimension of spin, which is 2. So there's a projective representation. You have to project down to make it equal to the spin Hilbert space. But let's not get into that detail today. But this actually makes the Kitaev honeycomb model solvable. Of course, when I write down, I am trying to solve it. I find that it is not solvable that as far as I can see, but I can still do this. So one of the things you would try is just write it in Kitaev representation, and there it what turns out. So here I will, from now on, I will actually start focusing on this 4-spin model, because it has a lot more structure that you can analytically exactly say. With this, you kind of stop here. You can't say much more, but this result that I'm going to say also applies to this model. Right? So let's take the 4-spin model. I have sum over all these new plaquettes. J mu have this. Right? Now clearly I just plug it in. I'll erase it, just it should be clear enough. You will get these 4 Majorana form. So you get 4 gamma zeros because you are from each. I'll gain KL. And KL. So even though we had this anti-commuting algebra in the spin variables, it turns out these are actually conserved quantities. Okay. So let's, right, so this object actually commutes with the Hamiltonian. Furthermore, from the, say this was X plaquette, I got a gamma X, gamma X, gamma X, gamma X from each X plaquette. I get a gamma Z, gamma Z, gamma Z, gamma Z from each Z plaquette. But because these are fermions and you have like, even number of anti-commutations, these conserved quantities actually commute with each other. Okay? So these actually commute. So this is important.
Gamma mu on the same side anti-commute, right?
On the same side, anti-commute, and the opposite Paname sides also anti-commute.
Right, opposite.
Yeah. But these are because if there are 4 Majorana forms, even number of Majoranas, they anti-commute. They commute. So this is kind of like what happens in Kitaev. This commutes, and whenever these are conserved, you can replace it by, you can fix their values, right? They commute with the Hamiltonian fixed factor. They are like effectively classical.
Wait, so this sum over mu, J mu, I didn't understand. The same Hamiltonian you're rewriting?
I'm focusing on the fourth version. Yeah, fourth.
This is
You're doing it Hamiltonian.
I'm focusing on the
So far you were
fourth.
talking about the J mu, sigma mu, sigma.
Now I'm talking about the fourth spin term on the plane.
Just about that.
Yeah.
Not that original.
Not the host. But it turns out this quantity also is present for the Ising exchange now. It turns out, but I'm not going to focus on it anymore.
Just so this 4 spin model, is it derivable from that exchange model, Ising exchange model, or no? It's a different model with similar.
Yes.
It's a different model.
It's a different model which has these properties. Other properties might actually be different.
And which of these two you told me just now is derivable is from the Sumo model and vice versa, the 4 spin?
4 spin is going to connect to Shumu. It's not derivable.
Right.
I'll come to it. The Zhu-Moore model is a paper by Shenke, Zhu and Joel Moore.
This will connect.
Connect to that. It's not derivable.
Okay.
In fact, this is at some level primary to Shumu. And after some block decimation, that will.
So that is a
emerge.
limiting regime of this.
It's not a limit, it's an exact regime, but it's, I'll come to it. I'll come to it. So now I can replace this by a number. Okay. On the mu plaquette, I have this, this is a fixed number, plus it turns out Majorana form, it can take only plus minus, it turns out. So it is a Z2 variable, we call it. It is still an interacting Majorana form, so it's not solvable by the known techniques. However, what we learn from this is that even though this is a conserved quantity, this is a projective representation. So you are actually allowed to do Z2 gauge changes of the following form. 0 or mu doesn't matter, let's say 0 or mu. And you can multiply a site-dependent sign. Okay, the spin variable is of course agnostic to it, but if you plug it in, you'll get a product of all these epsilon Z2 signs for these ones. So you can actually change the sign and change the coupling, but the energetics cannot depend on it because it's a pure gauge change. Okay, so it is in that sense there's this underlying gauge structure which is not lattice gauge theoretic. In the sense, what I mean by that is standard lattice gauge theory, you put the gauge variables on the midpoints of the links in the lattice. But here, this object actually directly belongs to the center of the plaquette. You see? Furthermore, its value cannot control the energetic. Now, you see, in standard lattice gauge theories, you have the link variables, which are the gauge degrees of freedom. The product of them is the gauge invariant flux. Here we have a plaquette object appearing by the structure of the Hamiltonian, which is itself the gauge variable. So it is the gauge redundancy has kind of become physical.
So locally, how does the gauge transformation act on the signs?
This one?
Yeah.
So
No, I mean on the values of the U's.
Value of the U's, it will be product of the epsilon on those lines.
But I guess the point is that if you change, one of them, it will affect this one. Right, something like that.
So
you can flip so that one can come up with some rules where you can gauge transformations can flip the four neighboring ones.
Yes, and it should be the spectrum has to be independent. Yeah. Yeah,
So
please.
in what sense is it more physical? That's a part I didn't, I said. It doesn't, it will not change the energetics by definition.
By definition. So what I mean by physical is, so the one case that I like to think about when I talk about this physicalizing is just a 1D Kitaev chain. Okay. तो उसमें भी आपका वो now the Ising parity on each bond is actually conserved. But in 1D you see that that's like the gauge variable of the standard Kitaev, right? Now the product of those gauge variables becomes the plaquette conserved quantity in 2D honeycomb, and that can affect the energetics. In 1D, these gauges are actually pure gauge artifacts. You can always shove it anywhere. Something like that. You think of it as that effect, but happening now in 2D directly. So I don't know what that means, but that is the structure.
Well, see, I give you a standard Ising gauge theory on square lattice. Of course, the energetics depends on the value of fluxes I put on that bracket, right?
Yeah.
So in that sense, they're still physical if you, but once I go to a sector, then I don't see anything.
Yeah.
So
what I mean
is this similar to that or is it more than
No,
that?
it is different. It's this discussion that I had with Abhijit or we had last time is that normally in gauge series you don't want to consider the gauge redundant copies as a distinct objects. Here the local Hamiltonian structure somehow forces you to consider these quote unquote redundant copies as actually physical copies. They're redundant because you can use this operator to generate the copy, but they are actual physical states. In gauge series, you don't consider them as distinct physical states. Two states related by gauge transformation are not distinct physical states. Here, what?
So this is the old high energy versus condensed matter. When we do gauge theory, there are different sectors and they have
This is just semantics.
energies.
This is just semantics.
Okay.
It's semantic.
No, I just want to make sure that that's
It's semantic. Semantic.
Is it something?
This is the reality. This is mathematical platonic reality.
Okay.
After that is semantics.
So if we did not have that gauge redundancy for the U, then you would have each degeneracy would be 2 to the 2n.
Or something. Or maybe not even present.
Bracket,
Yeah. Yes.
you have these assignments
Yeah.
of U.
Right.
And brackets are unit cells times 2.
Right.
And then having this redundancy reduces that number to 2 to the n. I think about that.
I have not thought through from this point of view.
Okay.
But maybe you're right. As you said, when you change the sign locally, it changes some neighboring 4 plaquettes, all right? So you only can count one.
Yeah,
plaquette
have
or
equivalent
possibly.
class. So
Possibly.
the n may
Right.
be reduced to 2.
Something like that.
From the 2n reduced to
Something
the
like
n.
that. Yeah. Something like that must be. I have not thought through. But if I want to connect it to lattice gauge series, I have a gauge variable sitting directly on the plaquette, which is somewhat unusual at least. Yeah. Yes, please.
What is the gauge transformation?
You take your Majorana operator and multiply a sign to it, plus 1 or minus 2. So plus 1. It can be done locally.
All of them or any of them?
Any of them. Local. It's a local transformation.
Okay.
That keeps the spin variable invariant. Therefore, the Hamiltonian is invariant, the spectrum is invariant
And this is a local thing is going to depend on what?
on the side. I'm free to do multiply plus 1 on this side and minus 1 on this side.
But if I multiply gamma 0 I by x, let's say minus, then that one term changes.
Yeah. And it also changes here. No?
Why you can multiply any banana, right?
No, but it's side dependent. So if you multiply it to gamma naught, you have to multiply it to gamma mu also.
All the gamma, okay.
Yeah. Sorry. Yeah. All the gamma get the same thing.
And are there, are you saying you don't measure gamma coordinate as a gamma?
You can choose to measure that also, but this is just a structure, a representation. It's a representation of that element. The point is, it reduces a little bit, but it is still a 4th Majorana interacting form. So you can't really solve it, but you know that there is this structure. And now you can compare. So for example, in Kitaev honeycomb model, it becomes, this is if you wish the matter sector, and that's a hopping. This is just an interacting form by construction. So it seems kind of a different object than the other known cases. Okay. So this was one thing. So this is one possible sort of Majorana representation of this model and all variations. So these conserved quantities actually exist independent of this, because these are essentially, if you wish, you have these local Z2 parity. You have fractionalized it and one of them stays conserved. So this actually also is agnostic to the local spectral structure.
So if
Hmm.
you put it on, all of these are statements about periodic configuration or
No, these are just local microscopics.
suppose I have an edge,
Mhm.
what happens there? Because you need this continuation to keep having this, right?
Correct. As long as you can write it in this form. If the edge respects that, everything follows.
It will not, because on the other side, it doesn't have a Z, right?
Hmm.
At some edge, I have
No.
a whatever X bond and I don't have a corresponding Z.
That will lead to its own degeneracy, because what you are saying is, suppose I had an actual corner here.
Yeah.
That is a free site, free effectively classical site.
Yeah, so I'm just asking, in the usual sense, we understand that there will be edge modes.
Right.
The edge mode structure.
No, I have not paid attention to such things actually. Yeah. But they will lead to some effectively classical variables on the edges, and this might have some physics of its own. Yes. Okay. So now the next, again in this I completely forgot to mention my collaborator. So this work has been done in collaboration with ICTS. I mean, actually, this part he contributed, but in any case, he checked the computation algebra in this part, which was very useful. And Roderick Moisner also helped me to keep straight and not make sure that I was not reinventing something. Okay. So these are the hidden commutants. So these are objects of interest because of some thermalization issues in condensed matter. That there might be some quantities which are not very apparent in the standard way of stating the problem, but they are there. They're part of the structure of the problem. So these are sometimes called hidden conserved quantities. However, note that it's a product of 4 Majoranas. So it is a local quantity on that plaquette. However, because it's a Majorana form, it actually captures a very sort of non-trivial quantum resonance happening on that plaquette in some convenient form for you. I mean, this is just a very heuristic way of saying this. What is this conserved quantity? It's some funny, like you can ask, what is this in terms of the original spin variables? There must be a procedure to recast this in terms of spin variables, which will be a very complicated object. And this is the economical way of expressing that.
So what happens to the projection that you needed for the physical? I mean, part of the problem is gamma knots are not quite physical because they would in general take you out of the physical Hilbert space.
You
by
don't,
just
no,
giving-
that works out same as Kitaev.
One minute.
Yeah.
You have doubled the local reverse.
Right.
So how are you, so now when you count degeneracy, you say that,
Yeah, so maybe that projection fixes that issue.
no,
you're saying.
but. So I should halve the degeneracy
Yeah.
per site.
Yeah.
What's the remaining?
So there is one per plaquette, right? Now there actually the number of plaquettes is 2 to the 2 times the number of unit cells.
Number of plaquettes is 2 times the,
So this is our unit cell.
yeah,
There are 2 such plaquettes.
yeah,
So there are 2 to the number of unit cells such quantities.
2 to the number of, no.
2 times number.
2 times number of
2 times
units.
number of.
Unit. Yes.
2 to the power 2 times number of units.
Right. Which is
Now
not
you're
matched.
going to divide it by 2 to the number of sites, which is 1, how many sites?
4 sites per unit cell.
4. So you have to divide it by 2.
Yeah.
The
Looks
4 times.
bigger number of units.
So then,
Looks bigger, but.
Yeah, so how is this working?
Yeah. I have not worked this out, but I'm
No,
sure.
no, I just want to make sure some things just be survive.
Okay,
I don't
let's
want to
do.
implement it.
Yeah.
I
Let's
don't
let's
want to
Okay.
round for.
let's do.
So 1.
So the point is, so here's the point. If you change this sign, Kitaev, if
Yeah.
listen to me, if you change this sign, then this quantity will also change sign and this quantity will change sign.
Sure.
So therefore, they cannot be independently changed. So it's not 2 to the.
वो सब ठीक है.
हाँ.
I'm talking more about the fact that by writing sigma mu as I gamma naught.
Right. Right.
Each gamma is a square root 2.
Right.
You have 4 gamma.
Right.
Square root 2 to the power 4.
Right.
Is 2 squares.
Right.
It is 4.
Right.
So the local Hilbert space is now 4 dimensional.
Right.
Instead of, no, you got that up for later. Acha, local Hilbert space, I'm just saying, is 4 dimensions.
Correct.
But the local Hilbert space originally is 2 dimensions.
Correct.
So you have doubled the local Hilbert space.
Correct.
So everything you count
Right.
has to be divided by 2 to the number of sites.
Correct.
I'm just asking you to do the division and tell me how many states survive. What is the region that survives? So I should divide by 2 to the number of sites.
Yes.
Okay. Now in terms of your unit cells, I
Yeah.
don't know what is number of
There are
sites.
4 sites per unit cell.
4 sides,
Uh,
4 per unit cell.
4 per unit cell. So you have this as one side.
One side, and then there are.
So this is one, and this is one. So 4 sides per unit cell.
I see, because you're saying those middle sides are divided by 2, so you get 2.
Right.
And then the 4 corners
Right.
are shared among 4, so 1.
Right.
Okay, so 4. So 2 to the 4 times the number of unit cells is the denominator
Correct.
of the degeneracy.
Right.
What is the numerator? It has to be
Numerator.
more than 4 times number of unit cells. Otherwise, you will have no degeneracy.
I understand what you're saying. Yeah.
Huh.
So it's not right.
All we are saying is it more than 4 times number of unit cells?
So it's not
Otherwise, the degeneracy is an artifact of writing it in terms of matter.
possible. Yeah. So it's not. I agree.
It will go ahead.
I agree.
No, but
I
is
agree.
it an artifact or is it not?
I have to think about it.
But it was clearer in the spin language that the
Yes.
degeneracy. No?
Yes.
So they're going to Madonna as complicated like.
From this counting point of view, but
Yeah.
it exposes this hidden commuting structure.
Right.
So,
But
but
in the original language, you know what's the reasons,
Yes.
because there's
Yeah.
no division.
I agree it should work out. I agree. I just don't know the numerator is all I'm saying. But
No, acha, but you know the answer.
I know the answer. This is the
Which is
answer. This is the answer.
2 to the number of,
Unit cells.
but we are to the number, so therefore it should be 2 to the, in this language,
Yeah.
it should be 2 to the 5 times number.
Whatever. Yeah.
Each and 4 times.
Maybe reverse engineer तो आप कर सकते हो, but
So
from
how,
the representation, yes.
right, so
Yeah.
it should be 2 to the power now 5 times.
Greater. Yes.
Yes, then it will work.
Yeah. Powerful. Yeah. I'll have to think about
The
it.
reason it's hard to see where 5 will come up.
Kind of 5 comes.
Five
But it looks like
So tell me.
It's like U, right? I mean, U, the sign of U, you give that degeneracy, so every unit cell has 2 of that.
Right.
So it's like 2 to the power 2n.
But
So
it's all
4 to the n.
interlinked. It's all interlinked, you see. So it might have its little bit not trivial counting. I have not done that model, so that's why I'm not able to answer. Yeah.
So how did we get to the power mutant set in that original language?
You choose one set.
And the other is fixed.
The other generates the degeneracy for you.
Yeah.
ठीक है. So now we will go to the next representation theoretic, which is connecting to the U stuff. So we remember that there are these conserved quantities. And here, so another thing, the reason which put me on this track is, even though there is this liquidity, it was not evident for me because these structures had such similarities to Kitaev honeycomb model and Kitaev toric code that if there is anything topological or non-topological, there's something called topological degeneracy, we'll encounter that. And so at the back of my mind, it was always an issue, is there a, and even more standard motivation is there a standard lattice gauge theoretic perspective on these things or not? And that doesn't seem to be the case. However, there will be a topological degeneracy also hidden in there, and then there's something called this, but it's not a standard lattice gauge. Okay? So we will focus into this. And whatever we have discussed is agnostic to the sign of the couplings also. Right? So now, so here I would like to make a small point that the local spectral structure can actually matter a lot. And this leads to some simplification similar to Kitaev toric code. Kitaev toric code I'll maybe spell out at some point, but it is another class of models which does not have anti-commuting algebra. It has another set of commuting algebras, and you can solve it to some simpler techniques. Okay. But this has a family resemblance to the Kitaev toric code for whoever is in the know. Let's not worry about it. Now the question is, what is the local spectral structure of this object? So if I had Ising coupling, on a plaquette, right? Then the spectral structure actually depends. So if it is just nearest neighbor, then it does not quite depend on the sign of the coupling, and you have, let's say, 2 ferromagnetic or antiferromagnetic ground state, you have 6, and some local structure like this on the plaquette. And this actually kind of impedes progress in a certain sense, which if I take this, the local spectral structure is 8. If you wish, I've taken the conserved charges and made the Hamiltonian out of that. Okay, if you wish. So I have 8 states, 1, 2, 3, 4, 5, 6, which have +1 for this. and 8 states which have -1 value, right? And this has the following simplification that if I'm interested in the many-body eigenspectrum, the many-body energetics, actually the system doesn't care for the underlying spin configuration. It only cares for the product of them. So the system only cares whether on that plaquette, the value of this is +1 or -1, okay? And so this motivates defining a new set of variables to which the many-body eigenspectrum is going to care about. And we also know from our earlier arguments that the underlying spin variables are actually not doing anything very fancy. So we can kind of ignore them, and the physics is maybe at a different level for this 4-spin variant. So I'll define the new variable.
So when you say spins are not doing again, this is only for the dipole that sigma that the spins are doing something trivial, right? Sigma spins are most likely doing something non-trivial. You have power laws and stuff like that. Right, so saying that
it has to be consistent with this regardless. And the
it
fourth
has to be consistent.
higher spin correlators. Yes.
But because you are talking about the many-body spectrum, that's
Right.
where my worry comes from.
There's no
If we're
worry.
talking about the
We'll
one-body
talk about that.
spectrum.
Your question will get answered.
Yeah.
But the point is there's no magnetic order. That's all. Yeah. But this motivates defining a variable which is just sensitive to this, right? So the variable, let it be called tau mu. So on the muth plaquette, and for this I have to make a choice. Which of the x plaquettes or z plaquettes I want to work with.
But as you said, those will be your charges, right?
Those were my charges. Actually, the charges is sigma mu bar on this line.
So we broke half the
Right. Sorry.
I think I missed that part, sorry.
Which part? Which part?
So earlier you wrote down two sets of things,
Yeah.
and we broke half.
No, it's a sum over mu, no? So you have the product of 4 sigma mu's on the x plaquette, product of 4 sigma x's here, product of 4 sigma z's here, product of 4 sigma x's here, and so on.
But earlier when you had two spin couplings, like sigma x and z for all plaquettes. Now we have to.
No. It is again true that on this plaquette you have sigma z is conserved.
If you take sigma x on that plaquette,
That is not conserved. That is part of the Hamiltonian. It is not conserved. So it's not trivial.
then part of the Hamiltonian is not.
This is not conserved. This object is not conserved.
Okay,
Okay, let me write it down.
no, if you just commute that to that, it will be.
No, it's a sum, no?
It's a sum.
All over.
It has to commute with everything.
All the time.
So there'll be another.
Yeah.
You have to pay for the other mu.
That's exactly what I
Yeah,
said.
sigma mu bar, it commutes. Yes. So now I define this plaquette parity variable. I won't put adjective here. And the many-body energetic is going to care about this variable. And this is sometimes you can think of it as a block decimation. So it's kind of a coarse graining actually. You're not anymore paying attention to what is the underlying spin configuration. You're just paying attention to what is the plaquette parity. It's a form of coarse graining. Note, this is not the conserved parity actually. It is the non-conserved parity. Right? So now I want to write down this Hamiltonian in terms of this variable. So clearly, so we had two terms, right? Mu and mu bar. So for argument's sake, let's specify it to x. So I want to specifically choose x where I do this. So let me do that. So x quantities will clearly be, so let's put a capital I just to remind ourselves that we are actually on the coarse-grained lattice. It's this lattice. Now in the coarse-grained lattice, actually each x plaquette is the site of the new lattice. Is there a question there? No. Right, so this is that original x plaquette. So each x plaquette has become a site, I, capital J, capital J. And so all these sites, I have this term just by definition. Now I want to ask, what is the other set of plaquettes in this representation?
Yeah.
Right? So we can see that if I take 4 sigma x's, it is coupled by this 4 sigma z, right? So So this term microscopically couples this plaquette parity, this plaquette parity, this plaquette parity, this plaquette parity, this plaquette parity. So it's actually a 4-pin couple. Turns out. I'll write down the answer. It's not that hard to convince yourselves that. So we have these sites and then we have plaquettes. So this actually is an effective reduced square lattice, right? It's I, J, K, L belonging to the plaquettes of this square lattice, this reduced square lattice. It will be a 4 tau term. And it turns out that it actually just flips these plaquette parities, right? So because it's a sigma z, sigma z will just flip the parity. Actually, it turns out it's easier to see if you work with these spin variables. If I had set it up with z, it will just be immediate that whenever. So let me quickly do that. I apologize for this. So if I do with sigma z. So this was our Z plaquette, and there is this X plaquette connecting these things. Now sigma X acting on this plaquette will just flip the plaquette parity of this, right? So therefore it is this. And this, whoever has studied lattice gauge theory, unfortunately, I hope Vikram comes because this is where it's going to connect to Zhu-Moore model. This almost looks like the Z2 lattice gauge theory. Okay. However, the difference is this is not the Wegener Z2 lattice gauge theory. So here let's draw the lattice carefully. So this one I did a one-step block decimations. I had, and the degrees, this block decimated degrees of freedom actually live on the sides of it. That is the important point. And I have these 4 things of this. Now in Z2 Ising gauge theory, if you recall, not going to be relevant, so we can provide here. You again take any lattice gauge theory, but Z2 for our discussion, you generally like to put the gauge variables on the midpoints of the links, and that's just a convention. And then you take these kind of 4-term plaquettes for these. And then you may put a transverse field. So the Hamiltonian exactly looks like this, except the degrees of freedom live on the midpoint of the list. This, it turns out, as a local Z2 transformation. You can do a Z2 transformation on this star, change the signs, that does not change the Hamiltonian. Okay? So, but this block decimated Hamiltonian, the degrees of freedom actually live on the sides. Okay? So the question is,
these taus are living at Z plaquettes.
Yes.
And the interaction is happening at the X.
Yeah. So you have these 4 Z plaquettes, and their interaction is mediated by this X plaquette, right?
You could have done the other way.
I can do the other. So there's a duality. That duality, the Zhu-Moore model also has a duality, kind of like the Z2 Ising gauge theory duality में एक duality होता है. Zhu-Moore का भी एक duality होता है. Here it is obvious. It's kind of just this simple duality that we talked about. If I started with the other set of plaquettes, I'll get a, tau X on a different square lattice and a 4-spin term, 4 tau term, and they're dual to each other.
Sorry, I thought tau is going to be just a variable which is 0 or 1, right?
Right. Or minus 1 or plus 1.
So that's there in that there is tau Z appearing there.
Yes.
Then what is tau X that
It flips the parity. It flips from -1 to.
Oh, that's the definition of that tau X.
Yes.
Tau X is an operator.
It's a definition. Exactly. So it is coarse grained. This is actually, I'm not thinking of it as a 16 sized Hilbert space on site that. I'm thinking of a 2-dimensional Hilbert space.
Plus minus, right?
Plus minus.
Yeah.
And this is effectively just changing the signs of that. So it is an effective action of this term.
Okay.
And we have forgotten the degeneracy.
Okay.
Because we know what the degeneracy is about, and we can kind of mod it out. So this is kind of modding out that redundancy. So the redundancy is not unphysical, it is physical, but it is moddable out for this mod.
I see. So now the new one doesn't have any degeneracy?
It may or may not.
Okay, but that 2TM has been modded out.
Has been modded.
How is that?
It's not modeled out. You are not paying attention to it. You are just looking at the physics at the level of these variables.
Yeah, yeah.
So as of now, 1000 is a two cluster matrix, and if you choose to take into account individually, then
Right. So, yeah, that is a mathematical definition. But to address your point, Abhijit, maybe I will comment on this procedure if I were to do it not for this model, but let's say for the two-spin model, then it won't work out. But maybe it can answer your question.
But in this language, if I want to write commuting charges, are there local commuting charges?
No.
No. So in that sense.
No. So this is what is actually called this was worked out. This was studied by Moore. So just to point out, in the Wegner, so this is Wegner's Z2 Ising gauge theory. So the term is on these plaquettes, you have product of sigma z. I'm using the quantum information notation, and then on each side you put a transverse field. You see there are these quote unquote missing plaquettes, right? So it's as if those plaquettes are not missing here. Now, if you act by x here, that does not commutes with this and commutes with this. So this is a local gauge transformation. You don't have that structure anymore once you put it on a square lab. Right? Right. Very good. However, once Moore showed that this.
But is there a way to remove that kind of degeneracy there in this kind of language where you don't have any degeneracy anymore?
No, degeneracy. This is now gauge kind of a gauge redundancy.
Yeah, that's what I mean. So gauge redundancy, or write it in a gauge fixed language. Here, in some sense, gauge fixed.
If you wish,
right?
Yes.
So one could try to find those variables on which the energy depends,
right?
As you were saying,
right?
And just remove that degeneracy that follows from that empty plaquettes.
Yes.
In the same kind of. Same kind of way that you did here.
Right. Oh, you're saying if I put something here, can I lose the local gauge structure?
Yeah.
Yes.
With some variables.
Yes. You can always lose a local gauge structure. Yeah. Thankfully for us, me and Harsh, in fact, Harsh found out this connection that this is actually was studied by Moore. I initially got very excited. I found the Z2 Ising gauge theory hiding in there, but then in the discussion we realized it is not Z2 Ising gauge theory. So they actually worked out what are the consequences of this. Okay. So here, as we said, on this star, so this is a gauge transformation for the Wegner's theory. This commutes with the Hamiltonian, so you can keep, so this is like you want to maybe keep the redundancy or not, that's a different matter. But you see, the number of these gauge generators is actually 2 to the number of unit cells. So I'll just usually set Lx times Ly. So this is any time you have a local gauge structure, it is generally, number of unit cells, right? 2 to the, when we're writing 2, that's the number of symmetry. Yes. So from that point of view, it does not have a local gauge structure, but there are symmetries. Okay. So the symmetry is of the following type. If I take this row, right, and if I just consider the product of tau z's on this, that commutes with this, again pairwise anti-commutation, and it commutes with this. So there is a tau z product. It's like again a chain Z2 parity, which has emerged in the tau variables. Okay, so there are these in the tau language. There are these symmetries, if you wish, but conserved quantities, and the number of those conserved quantities are 2 to the Lx plus Ly. So it's not number is Lx plus Ly. The values they can take are 2 to the this. So these were called by Zhu and Moore. These symmetries were called sliding symmetries.
You're not with class,
Huh? You could do more. Yes, I guess. You can multiply this and move it down. Yes.
But this thing appears in fracton kind of thing, right?
This fractons, what they try to do is they want to Yes, yeah, you're right. Maybe sliding symmetries are present in fractals, but I'm not completely clear on the details. But generally, the fractonic models have a local commuting structure. Here, you took an anti-commuting quantum spin liquid, you block decimated it. The force spin this is very special to the force spin model, has this sliding symmetry business. Okay. So now the results are basically you have these sliding symmetries, which is like, let's give a notation. Product over a row or something. So OZ is the conserved thing. And this is it's like a global Z2 symmetry of the Ising model. Just in quantum Ising model, you have a global Z2 which can spontaneously break or not. Here, these semi-local, they're not local, but they're not global, they're like system width spanning.
Subsystems.
Kind of a subsystem. The subsystem symmetries can break. So the result, this was U mode. These symmetries may spontaneously break or not. Okay, and that depends on the details. And the answer is when this dominates, these symmetries are unbroken. When this dominates, the symmetries are broken. Okay, that's the answer. And there's a way to capture, and this is not a local order parameter, to capture this order when it breaks. Actually, it turns out you need a non-local order parameter very similar to Wagner's. In Wagner, if you know this theory, Ellipsoid's theorem, as you said, you cannot break any local symmetry. So therefore, you have to consider Wilson loops. The expectation of Wilson loops, depending on where you are, might have a perimeter scaling law or area scaling law. Here, what happens is you have such a loop object, which may have a non-zero expectation value or not. The scaling they don't talk about, and I don't know the answer. But the answer is simply it's not like whether it scales as area versus perimeter, whether it is 0 or not. That's what comes out to be the answer. And that's been spelled out in this paper. The reference is
This must be only for 2D.
This
If you go to 3D, because the corresponding things here would be either order 1 or 0. Because if I just think of the 1D loop, the perimeter is essentially going to be ordered n to the power 0 objects for each one. So, and that's why it would look like a 0 non-zero object. If you went to 3D and you had a sliding symmetry, you basically have a surface. So you will still have things which will go as n to the power t minus 1 versus, and then the answers I don't know that. Looks like okay. Then the answers are not 0 or in some ways you have reduced it to an effective 1D problem. So your perimeter in some sense is ordered 0.
I see what you're saying. Yeah. So these guys definitely focused on the 2D model. 3D, I don't know, maybe some Paulis kind of argument can invalidate or change the physics, but I don't know the answer. But this is the answer. However, there is a duality, right? So actually there's a duality between them. And that duality we can easily see. It's just the duality of which set of plaquettes you want to start with. Given that you have a four tau term, the opposite, right? It's that duality you can actually see in this language. There's a duality transformation which will convert this single side term into a 4 tau term in the dual language and single side term. Oh, they have worked it out. There's one, so there's a self duality. So this is when it connects to the transition and all those things. So whenever you have self duality at the self dual point, when these two couplings, the couplings, are equal, you expect a quantum phase transition, which was the intuition even from the beginning. That you have these degeneracies, but when the coupling becomes equal, they all maybe collapse onto each other.
Yeah.
And there's a gap. There's a furthermore one additional result which was worked out by Nusinov and Fratkin. And they can map this U model to a what is called a 90-degree compass model. The 90-degree compass model is you take a square lattice. You have no four spin or tau terms. You have only 2 spin terms. And it's imagine you have an Ising chain along x direction this way. So like sigma x plus sigma x, sigma x plus sigma x, sigma x. But the same thing along z direction. Okay, so this is called the 90-degree compass model. These guys were, and you see on these chains, the product of tau, sigma z is conserved. On these chains, the product of sigma x are conserved. This kind of like sliding symmetry. So they worked out how to map this into this node. This is interesting for me because on this chain, the Ising parity of this chain actually anticommutes with the Ising parity of this chain. So therefore, there's an anticommuting perspective there. However, because these are non-local objects, the degeneracy that you can generate is actually just twofold. We could generate an expensive degeneracy, which because the local charges were all, the conserved charges were all local, but anticommuting. Here you have conserved charges which are system width spanning, and therefore they kind of interlock into a grid, and it does not lead to.
Wait, you're talking about, you're comparing it to your original model.
Yes, now I'm comparing it to the original.
But in this model, it's very similar, right? It's tau model.
Yes, so at the level of this, it's so here you can't even say anything about the degeneracies, except
But
maybe.
why can't you, because as you said, there is
But these are all tau z's. Product of tau z's here and product of tau z's
Oh, I
here,
see.
which commute. So you can't say anything. But through this mapping, you can say maybe there's a twofold degeneracy. I don't know. I'm just saying.
Sorry, but when you have this product of tau z, but you still have those many conserved charges, right?
You do, but they all mutually commute.
Yeah,
So then you can't say anything about degeneracy. It's just a sectoring of the Hamiltonian into blocks. But whether two blocks are degenerate with each other, you can't say when you have commuting charges.
but they commute to the Hamiltonian also, right?
Yes. Yes.
But then that means you can diagonalize Hamiltonian and the charges together.
True, but
And then you have 2 to the power Lx plus Ly degeneracy. Why not?
no, if they are indexable by the values, these are the two quantities. Each eigenstate will be indexable by plus minus one of these conserved quantities, but they are whether they are degenerate or not, you can't say it. Okay, I'll talk about it. You will see. We'll just discuss this point from a slightly different angle now. Okay, but this is, if you wish, this 4-spin quantum spin liquid, its many body order is of the Moore type, which can spontaneously break, but those order parameters are actually non-local order parameters. They are also not local, so they are like kind of non-standard from standard symmetry breaking point of view. Okay, I hope I'm not losing some audience. But now I will also now argue that this 4-spin model is interesting because there is a topological degeneracy also in the model. We can argue it, and I'll go through that argument now. And that argument actually works at the level of the original sigma variable. Okay. So I'm thinking, what should I erase? Erase. And it's very interesting. So, some aside, you take the Wegner Z2 Ising-Gauge series. This is not solvable because you have this 4-spin term and this is x which don't commute with each other. You don't know how to solve it generally. But one way of looking at topological order, what is called this Kitaev toric code. I don't know if you are motivated by this or not. You can replace this single site transverse field term by this gauge generator itself. Okay, just on this slide, you erase this, and on the stars, you actually put. This is a Hamiltonian. Obviously, as we said, these are gauge generators, so they commute with this. They are all mutually commuting. This is what is called the Kitaev toric. Okay. Now, Kitaev toric code is very interesting for Tennis matter people or quantum information people because Kitaev showed that this has a what is called a topological degeneracy. And there are many nice arguments to see this degeneracy. I'll give you one argument, kind of this anti-commuting algebraic perspective. But those degeneracies are not splittable very easily. And therefore, it was thought that they might be a good platform for implementing quantum qubits, which are fault tolerant, robust to local errors that the environment might want to induce. But these degeneracies are hard to split. I'll comment on it. In this 4-spin model, what we are going to see is that there is a form of topological degeneracies in the original variables. However, there is all this extra degeneracies, zoomorphisms. And one might wonder if they have some implications for quantum information type thing. So if anyone works on those kinds of things, I would be very interested in chatting. So now let's get to it. Let's forget about this. So now we'll just work directly at this original level. And I'll actually, just to set the stage, I'll actually quickly do it for the Kitaev toric code, maybe. Or not. Yeah, let's do it. With Kitaev toric code, and it turns out that the toric code is believed to be in the same universality class as the Z2 Ising gauge theory, and it's a solvable version of that. No. So I have all these degrees of freedom at the midpoint of the bonds. Just as these sliding symmetries, we can try to identify if there are such symmetries in this model. So here, maybe to wake up the students, can you identify any symmetries of this form that in this model? The model is this. Product of z's on these, we have the 4-spin term, z. These are called plaquette terms, and on a star, you have a product of x. And I'm claiming there are these kind of chain conserved quantities in this model. Can you identify? The trick is always whether you can make things pairwise anti-commute or anti-commute. That is the only trick in this. Whenever you have these Z2 models. Okay, so let's draw one line. So if I draw this line, you see it shares two sides with each plaquette term, but it shares a single side with the star term. So therefore, I want to make it commute with the star term, so I'll put product of x's. Because the star term was made out of x's, and all the plaquette terms have 2z, so there's pairwise commutation, and x ho gaya. So this product is actually a conserved quantity. This one. Okay. So on this row, OX is conserved, and all these rows, OX is conserved. But as you said, you can move things around. So for our discussion, you can focus on one unique thing. Rest are all related to each other. By a very similar argument, you will have this OX also conserved. And now we can take this other kind of row. And you can now guess the answer because it is sharing a single side with the plaquette term and two sides with the star term. On this row, it will be a product of Z. It's conserved. Correct? So I have such 4 non-local symmetries.
So what about
They are also present, but they are not unique information. I don't think you can. So the point is, when we consider two things separately, if you can't multiply by the existing local conserved quantities and convert to each other.
No, I'm just saying that if you have an operator which is supported along the line, those will also commute with these things.
Yes, yes.
Okay, but you are saying what?
Well, I'm saying that you can build them by taking one of this and multiply with the local object that you have in the tree. So therefore, it turns out these 4 things are the distinct things. So you take OX.
How many times you work crossing and so make that.
Right? Yeah. Yeah. So we identified one, this was my OX, this was OZ, and there's a OX here and OZ here. Right? So there's horizontal, vertical. Now we can work out the commutation relations. OX horizontal will commute with OX vertical. This is not a new argument, it is actually in the original paper of Kitaev. And there are a bunch of commuting things, but you can also identify anti-commuting things, right? So for example, this OX and this OZ share a single side. And vice versa. Okay? And by the very same arguments of anti-commuting operators generating degeneracies, this actually gives you a fourfold degeneracy. There's another set of this. And these are very important for the physics of the Kitaev toric code model. There's some mutual statistics, business, etc. But from our point of view, once you say me this and then each of them individually commute with the Hamiltonian, we are forced a fourfold degeneracy. And why should you consider it topological? Is because of the following reason, that you can index your eigenstates by, let's say, one set of plus minus one. You choose one of them, non-commuting ones, right? And you can ask, how can you split that degeneracy? Okay, so how can you split that degeneracy? The Hamiltonian, of course, they conserve. So, take it. Thanks, Abhijit, for coming. So they're degenerate at the Hamiltonian level, but you might want to split the degeneracy by putting some extra term in the Hamiltonian, some extra local term, like the transverse field. Now, in the perturbation theory sense, two such degenerate states have to be connected by the perturbation, right? But if it's a local perturbation, you need infinite number of local perturbations to connect the two states. Okay? This is the original argument of that. So therefore, it's called a topological degeneracy because the splitting of these two states is exponentially small in the system space. So if you make it big, the local perturbations can't split it that easily. This is why you should consider it topological degeneracy. So now you might guess, I'm just going to identify such operators in this four-spin quantum spin liquid. And it turns out they exist. So let's do that. So let's just recap. This four-spin.
One question, this is a technical question I forgot. Was Berkeley's argument there in Wegener's paper or not? Had this star and plaquette was there. I forgotten.
No, this is not, so Wegener didn't have the star. It defined even
And
the icing state.
Forward's review article has the star.
No, but I don't think they thought about it. They don't even think about topological degeneracy at that particular time. It was not even a concern for them. And Kitaev really had this fault tolerance point of view, which forced
For the toric code, yes.
yeah, from a quantum information.
So we've asked a lot of questions.
Huh.
You're at 1.5 hours.
So when should I wrap up?
How are you situated?
I can wrap up pretty much.
Is there a natural wrapping up point?
Yeah, after the topological degeneracy rest, I can say in words.
Okay.
Yeah, so I can speed up now. Well, I was under the impression that these have no time limits. The space
It's
time.
always lunchtime.
So okay, let's do that. So let's just to recap. This four-spin model, among other models, has this extensive degeneracy and quantum spin liquidity. It has this U-Moore physics, and then it has this additional topological degeneracy. And so the question is, again, you have to identify these non-local operators. So you just remember that there are these four spin objects here. So again, pairwise anti-commutation is going to be the trick. So suppose I take this. Now, what is the operator that I can write down here? Well, I can write down two operators on this horizontal row, OX or OZ. They're not both commute with the Hamiltonian because it pairwise anti-commutes with this plaquette and it pairwise anti-commutes with this plaquette, right? And the same is true for these ones. You take a row of this sort and OX on that vertical row, OZ on the vertical row, commute with the Hamiltonian and because of pairwise anti-commutation. And now it's trivial to identify this structure in this set of conserved quantity.
You can alternatively start from the square stuff you introduced earlier and then multiply, like make those bubbles bigger and bigger.
If you wish, there might be some. No, these are actually, you won't get through that. You won't get through that because these are on non-trivial loops. So imagine this is on a torus. So these are new informations actually. And they have this anti-commuting structure. So you can generate a four-fold degeneracy of this topological type in the original variant. So this is essentially the argument that there's a topological degeneracy in the four-spin model. The four-spin model you can say a lot, it turns out. Now in the two-spin model, you can't say any of this. There is no topological degeneracy through this kind of argument. The block decimation also doesn't give you this it does not give you. You can write down something, but who knows what the physics is. So therefore, the general message is you have this anti-commuting spin liquid class within which there are regions. A regime which has topological order maybe, a regime which has Joule physics maybe, a regime which has something else maybe. Okay.
So from the point of view of sort of realizability as people indicating, the two-spin is better than the four-spin.
Yes and no.
You can say about the two-spin, the more
True.
interesting.
True. I agree. So yeah, though that is one of my concerns as well, but I don't have any.
There's some limit where I make the interactions JU very different from each other.
Right.
You know, like I can derive toric code from Kitaev.
Right.
You derive your four-spin from two-spin in a particular limit by making one of the J's much bigger.
You can, but it is not very natural. But it's not very. I wrote it down, but it does not. It's not as elegant as honeycomb model reducing to the. Yeah, it's little unnatural for some reason. So we can almost end here. One final point I would like to mention is that this was all limited to this square lattice. So any non-bipartite lattice you can play this game. But if you were to play the same game on a non-bipartite lattice on a sharing, so Kagome is one of our favorite ones, where the answer turns out, you have the extensive degeneracy, you have topological degeneracy for a 3-spin version. This, and you have spin liquidity. But in this plaquette parity variables, which is now a 3-spin term, when you do the block decimation, it becomes, so you choose, let's say, these ones specially, and then you see it forms a triangular lattice. So the decimated lattice is actually a triangle. I click KL. And now it turns out because it's edge sharing lattices, as far as we can tell, this actually has a 3 sublattice order in it, in the plaquette parity variables. That's what we find. So it's not clear whether Joule physics directly applies here or it's a 3 sublattice spontaneously symmetrically broken order in terms of these plaquette parity variables. And then you can have a quantum phase transition because there's a single side term there and this product. So you can have a 3 sublattice melting transition of Kitaev potentially in the Kagome lattice version of this. Now it's a quantum phase transition. I don't know what the original context Kitaev had, but if the quantum phase transition will be of this 3 sublattice order melting time. So this is one new additional result, and you can play the same game for pyrochlore in 3 dimensions, blah blah blah. And we are including those results in the upcoming paper. But this is the main message, that you take these models and somehow so many new things come out. And there are perspectives related to thermalization and fragmentation physics. There are perspectives related to quantum error correction, qubit codes from
in so many sectors, there is no conventional thermalization in any case, right? Without the Lama term.
Right. So you have to put a small thing and then start asking those questions.
But without asking those things, is there some analog about Gautam and all? What is it? Generalized?
Basically, you thermalize within a sector.
Yeah. So that you have to check. So the simplest thing is you go to one block and check for level strength.
Yes.
So that is very useful.
In your one block, don't you actually want to have complete degeneration? So you don't have Hamiltonian forming.
Now you'll have to break that without breaking the sector.
Without breaking the sector, you have to generate a Hamiltonian.
Right. So here maybe one final point I would like to mention, which is what Kitaev's complaint, if you wish, about these models. So here, when we have the anti-commuting structure as block diagonalized, but each block has the same many body spectrum, right? That may or may not be satisfying to someone. So you can ask the following question: can I arrange for a situation where you have this level of block diagonalization, but they are not equidegenerate? And Kitaev has a construction where you can do an SU2 symmetric model where the energy spectrum is not the same everywhere, but the Hamiltonian does respect this block diagonalization.
But you can't say anything.
You can't say much, but it will have its own.
Trivial to say.
it has its own set of physics. So it's not
That
pertaining
is
to that.
understandable. If you get there, things get more. No, in fact, I wrote it down for him immediately after he gave the talk last time.
Right.
But the point is, once you make it contribute, you can't say anything.
So that's the challenge. But it's a different physical object is another way of saying it, which might have its own intrinsic
you
value.
get Taylor's model in some limiting case where you might be, which is not realistic, but maybe you have some small parameter which allows you to do some
No,
particular.
there's no model written down here as a.
Actually, the one I wrote down was just SU2 symmetric bilinear coupling.
Correct.
Now I fixed the signs up.
Sign,
Yeah.
like
So
that.
SU2
Some are
symmetric.
antiferromagnetic, some
No,
are magnetic, and I can make this happen. And then I know nothing about each block. I can block that. That's already a non-trivial statement, but I know nothing about what happens in a block.
Right. Standard Heisenberg model.
The standard non-trivial quantum many-body system. Right. Which I expect will come like do everything now.
Are they like correlated blocks or it can be completely random?
Each block will be quite different. I mean, each block, I can write it out for you something.
Yeah.
It's just literally nearest neighbor s dot s, and I mess with the signs.
Well, yeah. Okay, thanks a lot for coming. I hope you got something out of it.
No, thanks. So it has developed further from that.
Yes.
So hopefully the next version we just read in a journal.
Yeah, no, for sure. Yeah.
We have not written this up fully yet.
This is not in process. This should be out on archive within a month.
No, it's not in a journal.
Journal so hoga.
Does its force-spin term come symmetric with the Griffin?
Huh?
Does the force-spin term on its own have some symmetry with the Griffin term?
Right. Read again.
Does the force-spin interaction have a symmetry? Does the two-spin interaction do so?
They don't. So these ones actually don't exist for this full spin, two spin term. So you see, say I take this quantity, right? If I have the two spin term, there's a Z link going either in this direction or this direction, which is anti-commutative. So two spin actually this structure is absent altogether.
But they only come as okay.
Yeah. So the four spin always help because you can arrange for pairwise anti-commutation much easier than two spin.
So when you guys were talking about two spin versus four spin, I thought the difference was that like when you estimate it, you have like you generate two spin interactions.
Right.
If it has this extra symmetry, is it that bad?
Yeah, I don't know, but let me tell you what if you're talking about how the block decimation would work out for two spin.
Can I use the term technically natural?
Say it again, natural.
Technically natural.
Technically natural.
People are worried about the Higgs mass being like diametrically generated, so you have to worry about it, but the fermionic mass doesn't, the zero mass symmetry. This sounds like that, right? Like if you don't, if this sounds like it doesn't enhance symmetry, so when you decimate it, you like generally, and also once you manage to achieve this experimentally somehow, do you have to worry about small perturbations?
I see. So my perspective is the following. So we have this highly degenerate spectra, right? Now so the general perspective, once you put a perturbation which voids the anti-commutation algebra, how much of the physics still survives?
Yeah.
So it is not hard to imagine that we will get a band of this sort, and so on. Now, if you are at an energy scale or temperature scale, it is less than this width. I believe all this liquidity physics, etc., will actually fly. Okay,
That's fine.
that's fine. Now, what is the physics is a question in itself. It might even be sensitive to perturbations, but if for example, SYK like physics also might be relevant. So you can ask for the density of states of this little thing. It might be of the SYK form or non-SYK form, who knows? Now, with regards to the topological degeneracy, so the question you have to ask the following. So I had all this degeneracy, but then there is this additional fourfold topological degeneracy, right? Now you put some perturbation. The original subsystem degeneracy, if you wish, will split. The topological degeneracy will also split on a finite system. Now you have to ask whether there is a fourfold degeneracy which is splitting much slower than the other degeneracy splitting. Then under perturbation, the topological structure survives. And the general expectation is whenever you have these kinds of topological degeneracy, you expect them to survive for small enough perturbation. So the sort of range of perturbations.
But that's because it's a topological degeneration.
Yes, yes.
Why were you guys having the discussion between 2-spin and 4-spin track? Why not better on them?
No, it's only better because you can save little extra things more precisely.
Oh.
2-spin mein you can't say much. So 2-spin mein what you can say is
I thought they were arguing that 2-spin is better.
2-spin is better from a physical point of view. Right?
Yeah, that's
If-
fine.
Why is it better?
Yes.
Because it's easier to arrange for 2 spins to coupling or talking to each other in some material or something.
Literally to get started.
Yes, yes. So the 4-spin couplings, by the way, are not unphysical. So if you any quantum computer, like people who are actually putting money into these things like Google, IBM, etc., they routinely work with Kitaev toric. That is what they're trying to have 4 artificial qubits coupled in the Kitaev toric. Yeah,
But
Kitaev.
what materials were one thing different from, or are you saying that you need like specific? No, you do have materials where like one lattice interaction bonds differ from the other.
Yes. No, you do have, but there you see, just apart from that, there are many other effects in the Hamiltonian, and you cannot naturally get rid of them.
Yeah, that's why I was asking about the symmetry. Like, does the fact that this has a symmetry say it somehow these effects?
No. So you can never ensure that in your material, these 2 spins only couple along x direction and these 2 spins couple along z direction. The best you can hope for, it's let's say sigma x plus some small sigma z, sigma y. That is the best you can hope for. They will never be exactly 0. You have to, it has to be very special.
So you can't even make the say 2-spin terms now.
Yeah.
Okay.
Yeah. I mean, there's no natural reason. And you have to hope that you land in
And that's
that
a natural reason. There is no symmetry.
natural reason from a certain point of view.
Okay,
From a material specific point of view, the crystal environment has no reason to make this happen for you, even at a 2-spin level.
Okay.
Now, so therefore, these ideas actually, it's kind of quantum engineering rather than materials physics. You want to take some artificial qubits, couple them artificially, and then all these results, you can engineer in a setup and they might be relevant for some computation. That's where not particularly my ideas, but generally the community, that's why it's pursuing that.